Okay, we have seen how body-worn sensor has the potential to transform the way we assess mobility. However, the intrinsic technological limitation, the lack of standardization procedure, and the lack of robust validation on pathological population is still hindering the big jump from the lab to the real world. Today I will share with you some of the challenges, solutions, and lessons learned by leveraging the experience done in the Mobilise project. Few numbers to start with. The technical validation took 3 years of joint efforts between universities, research centers, pharmaceutical companies, technological partners. It is funny or scary to think that the total amount of time dedicated to the technical validation only, it is equal to one person working every day for 50 years to the same problem. And this very complex endeavor was masterfully led by ex-professor Claudia Mazzà. She left after the work package, the project, and now by Dr. Silvia Deldin. We have seen from the previous presentations that to get the full picture of the functional mobility, we have to integrate mobility perception, measures from the lab of motor capacity, with real-life observation, which are, for definition, unsupervised and unstructured. And this is not an easy task at all. Why? For different reasons. First, signals, which appear to be very regular and easy to analyze for normal gait, then may exhibit different patterns for different pathologies, depending also on the severity of the pathology. Second, when we move from the lab to real world, we realize that gait is not straight. It includes indoors, outdoors. The patient may use walking aids, and he had to face with transferring from and to a car. So it's really very complicated. So from a technical point of view, the analysis complexity increases from moving to the green base of the pyramid for straight analysis of straight line level normal walking to the top, which is the analysis of disease gait in free living conditions. And this is where the Mobilise project was called to contribute. So, as technical partners, we had to provide valid, technically valid methods and tools for describing digital mobility in real life. And hopefully to finally reach the position enjoyed for many years by other disciplines, for instance, cardiology. To move from the comfort zone of the lab to the wild, real world, we had to face a certain number of challenges of different nature. The very first one was a problem of definitions. To agree on definitions is very important. And if you don't, you can experience dramatic consequences, as it happened in 1999 when the Mars Climate spacecraft was lost in the space just because one team of the NASA was providing data in meter and the other in feet. Literally lost in translation. And the NASA lesson learned, we realized very early that we needed to define a common language. We therefore considered several aspects related to real-world mobility. And for each of these terms, we identified these terms, and for each of them, we tried to define a thorough and precise definition with the intent of building a consensus based on expert opinion. For example, what is real world? What are the peculiar characteristics? What is walking? And what is the minimum definition for walking bout? Especially the last point is very important because it's crucial for allowing to aggregate gait sequences. It was decided that a walking bout has to include at least 2 consecutive right and left strides, 5 steps. Walking bouts can be separated by a resting period, which can be anything like stopping, sharp turning, or any other activity. And in this way, we could aggregate different walking bout. And then within each walking bout, we could define a set of digital mobility outcomes. And for each of them, we could define an operational definition, a very precise operational definition. Just to clarify with an example, we have a general definition. Walking speed, for instance, walking speed, which is the primary outcome. Walking speed defines the person's rate of travel by identifying the time required to cover a given distance. But then from this very general definition, we need to define a formula to compute the parameter gait speed. And if we look at the literature, there are different definitions at stepwise, stride-wise, path-wise level. And the problem is that all these definitions are correct. But then if you use different definitions, we will have the different numerical description of the same phenomenon. And this is, of course, is something that we want to avoid. The second challenge was about choosing the ideal device. Ideal, yes, but from which perspective? In terms of accuracy, in terms of wearability, or in terms of the data collection? Technology-wise, based on the requirements of the Mobilise project, that is to collect real-world data for 7 days and to extract, to provide a full description of mobility, we opted for the use of a single inertial measurement unit, including 3-axial accelerometer and 3-axial gyroscope. This choice was quite straightforward. A more strategic and critical decision was about the best location, the best device location, which also influences the attachment modality. In fact, there are different options. You can attach the device to the lower limb. This solution is quite accurate, but relatively invasive, or to the torso or upper body, or to the upper limb. For instance, very popular location is the wrist, but then it's quite difficult to distinguish between and discriminate between walking and non-walking activities. And of course, each solution has pros and cons, and to take a decision, it was then implemented an objective selection methodology. We identified 4 different domains for real-world mobility, and then for each domain and each item, we define a weight based on the opinion of experts from different backgrounds. We define also a scoring system, and this procedure allowed to compare and to rank the different possible solutions. And it occurred that the best trade-off solution was to use a single unit attached to the lower back. Another important issue was the assessment of the quality of the raw data collected using the inertial sensors. We developed a testing procedure that we used to test each single unit we used for the project, 72 devices, and to provide a description of the stochastic and deterministic errors, and to provide a statistical description of the noise of the sensors. This also allows us to compare the device that we were using for this project with other commercial devices. Why it is so important? A thermometer, to be used in the clinical application, must comply with performance standards. This is not the case for digital mobility device. At the moment, there are no international standards for digital mobility device to be used in real world. And it is, of course, very unspeakable that this situation, things will change in the next years. And we think that the work done during the technical validation can be very helpful in this sense. Furthermore, this is also very important because if we want to develop, we have to keep in mind that we want to develop a sensor agnostic solution. So this is really crucial. We have a common language. We have a device for collecting data. Now the problem is how to quantify real-world walking. In other words, we needed to identify and to implement the best algorithms to compute primary and secondary digital mobility outcomes. The preliminary step was to define a structure of data for standardization and storing, which is essential for effectively sharing the data with the community. And this is also very important in the light of developing machine learning methods, because for developing machine learning methods, you need to reach a critical mass of data, and possibly from different and heterogeneous sources. The standardization data were then fed into this computational pipeline. This slide provides an overview of the different blocks, from gate sequence detection, pre-processing for signal enhancement, step length, then stride level description for identifying the eligible working bounds, and then to extract primary and secondary digital mobility outcomes. More than 80 algorithms were selected, implemented, and compared. This is a huge work carried out by the team of APFL and Erlangen University. Another challenge was to face how to test the algorithms to be confident that the digital mobility outcomes that we were extracting were technically valid, under, of course, the condition of end use. As we could not find anything in the literature appropriate, we had to develop a 3-level stage testing, which included in-lab assessment, 2.5 hours acquisition and free living, and 7 days of real-world monitoring. We considered different cohorts and from different regions and cultural contexts. So one quick question: what is, in your opinion, the most difficult population to analyze? Older healthy adults, Parkinson's disease, multiple sclerosis, congestive heart failure, chronic obstructive pulmonary disease, proximal femur fracture. There is a little hint. Look at those numbers. What do those numbers represent? Lynn? Those numbers represent the number of subjects within the cohorts that were using a walking aids. And as you can imagine, proximal femur fracture were the population exhibiting a more asymmetrical, slower, and difficult to analyze gait. We first used the in-lab assessment to test the algorithms under very highly controlled conditions. Data were collected in 5 clinical centers using as a reference system optoelectronic stereophotometer system, which is composed by multiple infrared cameras. And in order to standardize the data collected and in the clinical center, we performed a spot check for assessing the accuracy of the stereophotometric system, both in static and dynamic trial. And we also implemented a spot check for minimizing the effect of human errors in management of the files, thanks to Kirsty. The experimental protocol was designed to be acceptable for the patient and to allow to include enough and heterogeneous type of gait data. To fulfill these requirements, we included 7 different tests at different velocities, including turning, sitting and standing from a chair, working at different surfaces, passing obstacles, and we also add another activity aimed at simulating those activities usually performed or expected to be performed at home, including moving object, chair, watching TV, etc. And as you can notice, the proposed protocol allowed to capture for each cohort typical gait of data along with a broad range of velocities. Of course, similar to those expected in real-world conditions. This is an important point. The second level of validation protocol included 2.5 hours of free living and was used to assess the algorithm performance under unsupervised conditions. In this case, we use as reference standard a multi-sensor system, the INDIP, which included pressure insole, magnetic inertial measurement unit attached to the feet and to the pelvis, and infrared distance sensors. In this way, we could directly measure the contact with the ground, and then by double integrating the acceleration, obtaining a very high accurate displacement for the displacements. Errors were very good, and we obtained a mean errors across subjects and tasks lower than 1.6% for gait speed. Then for the third testing level, subjects were asked to wear a device for 7 days for assessing wearability and acceptability. We also use a mobile app, Icora, developed by Professor Fabio Ciravegna, and we use this app for identifying the contextual factor, the more important contextual factor, and then using the information provided by the GPS, the Wi-Fi, and the digital maps, we were able to understand if the subject was working indoor, outdoor, or during the habitual path, or the slope. It looks easy, it seems easy, but it's not, especially because the quality of the data is affected by many issues that can really affect the final quality. The last but not least challenge was about to process and the huge amount of the data that were collected and produced. To compare the results provided a single sensor with the reference system, we first had to match the walking bout. So following a binary classification, a walking bout, if both systems were identified the same walking bout, we have a true positive. Otherwise, if on the single sensor system identified the walking bout but not the reference, a false positive, and vice versa, a false negative. Once, based on the walking bout matching, we could then perform, we could define a performance matrix, and then for each true walking bout, we could compute each digital mobility outcomes and define a criterion validity matrix. This could be done at walking bout level, subject level, or cohort level. Results were in general very good across cohorts and condition, and as expected, digital mobility outcomes improved when we consider longer walking bout longer than 10 seconds. This is quite obvious because especially stride length and gait speed are less affected for longer walking bout by intermittent gait. As you can see, the median errors does not change too much, increasing the walking bout duration, but the error variance a lot. Unfortunately, of course, for longer walking bout, it decreases also the number of walking bout, and this is a problem. Okay, before concluding, I just want to share with you some extra experiments that we performed on a very special participant. For this subject, we had to reduce the size of the pressure insole, but even with a smaller number of sensing elements, we were then able to correctly segment the gait even for this very unpredictable gait pattern. Okay, I want to conclude with a very big thank to all the people involved in the technical validation. It took a real team effort, but I think that we made it. Thank you.